In your last set of video lessons, you learned about writing reaction mechanisms. And we learned that that could always be written from the rate determining step, given that it was first. We're going to look at how to write the reaction mechanism today with a fast initial first step, which is also equilibrium. When a mechanism has a fast first step, the rate limiting step most likely is going to contain intermediates. Remember, intermediates are something that is made as a product in one step and then used as a reactant in a subsequent step. When that first step is a fast step, it is also at equilibrium. Once it reaches equilibrium, the forward and reverse reaction rates are equal. So at that time, the concentration of reactants and products are related, equal as well, and we can use that information to substitute out the intermediate in our rate determining step so that we can get a rate law that only includes actual reactants and no intermediates, as it should. We're going to go through an example to learn how this process works. We have nitrogen oxide reduced to hydrogen gas, and we're given this overall reaction equation and the experimentally determined rate law and a possible mechanism with these three different steps. The first step is a fast equilibrium step, and the second step is our slow step or our rate determining step that the rate law is based off of. We're going to go ahead and write our quick rate law for each of these steps. So rate is always equal to our rate constant times the concentration of the reactants raised to their power of their coefficient. Again, that's not going to be the rate law for the overall reaction because that's determined from the rate determining step. That's just the rate law for step 1. Rate law for step 2 would be our rate constant times the concentration of N2O2 and the concentration of H2. And for our last step, which is another fast step, which would be irrelevant to the rate determining, but regardless, we would have our rate constant times the concentration of N2O and H2. So to determine the rate law from those steps, we need the rate law from our slow step. We are still always writing the rate law from our rate determining step. So that is our rate is equal to our rate constant times the N2O2 times the H2. But this does not match the experimentally determined rate law that they give us. That's because it contains an intermediate. See that N2O2 is an intermediate because it was made in step 1 and then subsequently used in step 2, and it is not part of the overall reaction that was given to us up top. So we need to use our fast equilibrium step to replace that intermediate, to replace that N2O2. So our fast equilibrium first step will replace that. Remember, at equilibrium, the rate forward equals the rate reverse. Since that is the case, we can set the rate law for the forward reaction equal to the rate law for the reverse reaction. We already wrote the rate law for our forward reaction in step 1, so that's just our rate constant times the NO2 squared. We need the rate law for our reverse, which will be the rate constant times the N2O2. Well, our rate constants are going to cancel out, so the concentration of NO squared is equal to the concentration of N2O2. Remember, we need to replace that intermediate, replace that N2O2. Well, this fast equilibrium step tells us that it is equivalent to the NO2 squared. That's what we need to replace it with. So when we replace that, we get the rate law for the overall reaction, which matches the given experimentally determined rate law with that NO squared times the H2. So again, from that fast step, we see that the concentration of NO squared is equal to that intermediate concentration N2O5. So we're going to replace that intermediate in the rate determining step so that we only have reactants in our rate law and no intermediates. On the bottom of this page, you have 2 more practice problems. In these 2 practice problems, try them out on your own. Resume the video when you're ready to check your answers. For both of them, you are writing the rate law for the mechanism and finding the overall reaction. One more note on that overall reaction. All of your steps should add up to the overall reaction. So N2O was another intermediate here. We're going to add up to our 2NO, our 2H2, the 1N2, and 2 H2Os, which matches the overall reaction that was given to us initially. So again, give those a go on your own. Resume the video when you're ready to check. Okay, so on number 1, we want to write the rate law for the mechanism and find the overall reaction. So when we write the rate law for the mechanism, we need to be using our slow step, which is the rate determining step. From that rate determining step, we're going to go ahead and write our rate law. Rate is our rate constant times the concentration of M and the concentration of A. Well, we can't use that as our rate law for the mechanism because it contains an intermediate. M is an intermediate because it was made in the first step and used in the second. We need to replace that intermediate using our fast equilibrium step. So as we take a look at that fast equilibrium step, we know that rate forward is equal to rate reverse. So we can set those 2 rate laws equal to each other. The rate constant times the concentration of AB is equal to the rate constant times the concentration of M. Those rate constants are going to cancel out, so the concentration of M, our intermediate, is equal to the concentration of A times B. So we need to substitute A concentration times B concentration in for the M here. So when we do that, we get the rate for this mechanism, which is our rate constant times A squared times the concentration of B. We still need to find our overall reaction. To find that overall reaction, we need to add up all our steps. M and X are both intermediates. We're left with 2AB yielding CD. So this is our overall reaction, which our rate law happens to match the coefficients of. Be careful on that though, because that will not always be the case, but it happens to be in this one. In number 2, again, we wanted to write the rate law for the mechanism and find our overall reaction. So finding that overall reaction, we just need to add them up. NO3 is an intermediate here. And one of our NO2s will cancel as well. So we are left with NO2 plus CO yields NO plus our CO2. When we're writing the rate law, we see that our slow step or our rate determining step is first. That's really exciting good news. It makes this problem really easy. When the rate determining step is first, we can just write our mechanism from its reactants. Write our rate law from its reactants. So writing our rate law from this, rate is equal to our rate constant K times the, we need to use the whole first step, not our canceled out NO there. So that is going to be times the NO2 concentration squared. So this time our rate law does not match the reactants of the overall reaction, but that's okay because we wrote it from the rate determining step as we should since it was first. So there you have rate law with a first step. We got some more practice on page 35 you can try out and find a key for.